So let's now think about the model itself that I'm going to look at. So I've taken an exhaust. This particular model is loaded in 3 directions simultaneously, X, Y, and Z, but the whole thing's loaded in those 3 directions simultaneously. So you can see there are some rigid connections to various points, various fixing points on the exhaust. The Nastran job has been set up using solution 111, and the key input to the Nastran run is the positions where you're going to request frequencies. So in this particular analysis, the person that set this up requested Freq 1 and Freq 4 cards. I don't know if you're familiar with those, but Freq 1 is a way of equally spacing points at set intervals. So the first line is a Freq 1 saying, please put points from 0.1 hertz, 25 of them at 2 hertz intervals. The second Freq 1 says start at 50 hertz and put 22 points with 20 hertz intervals. And then the next line, the Freq 4, says put points around each resonant mode, and the NFM, number of frequency points, is 3, so put 3 points round every resonance. So with a careful choice of those Freq 1 and Freq 4 cards, you can easily populate the transfer functions of the system without using too many frequencies. The trick is to have enough frequencies to properly define the transfer function itself, but not have so many that you make the model bigger than it needs to be. Because if you double the number of frequencies, you essentially double the analysis time for Nastran. Okay. So the input file to our procedure, so we're assuming Nastran's been run, it's generated those transfer functions, it's been put in, those have been put into an OP2 file, and I'll show you that in a minute. We then set up our job using a control file that is shown here. This is pretty well everything you need. So this has about a dozen lines in it, and everything needed to define and run the job is included. So I'm just going to cover a few of the key points of this file, and then you've got this file. I put it in the FTP folder, so you can take this file, take the Nastran run, and modify anything you want in this file to see what happens. So the first line is VibeFat 777. That's simply VibeFat simply saying we are going to do a vibration fatigue calculation with a job number of 777. The last entry on that line is the job name, exhaust_run1. So everything that gets created, all the files will have that as a file name. Then the other items on this first line, CSV H3D is an output file request. It's saying write a CSV file with the results in and write an H3D file with the results in. We're going to read Nastran results, but if you repeat this with OptiStruct, you need to change Nastran to OS for OptiStruct. I've requested corner results, but more typically you would request center results there. By requesting center results, your analysis size probably reduces by about 5 to 10, depending on what kind of elements you have. And then the next item there, naught, is log level. That defines how much output you write at each output point. It can either be 0, 1, or 2. If it's set to 0, then you only write fringe results, plus something we call a log file. If you set it to 1 or 2, then you write additional information at each grid point, like, for example, the response PSD or the rainflow cycle count can be written by changing that log level to a 1 or a 2. The next line, VFTGDef, is defining things like what analysis method to use for the fatigue calculation. We're using something called Dirlik, which is the most common method for your kind of models, I would say. It defines how the rainflow count will be created from the response stress data. 100 is a filtering number. That number can be 100 or less. If it's set to 100, then the whole model gets analyzed. Anything less means that elements with very low stresses get reduced from the output, so that can be set to a smaller number to reduce your output file sizes. 631 is the material ID for the model, but if you look at the lines below, we have something called LSET commands, and those LSET commands are going to make that 631 on the second line redundant, because what we've done on the third and fourth lines is we've defined 5 sets 1, 2, 3, 4, and 5, and each set has its own material ID. and then below we're reading in another text file, set1.txt, which has a set of elements that go with that set. So so let me just show you that. So if I go to the location where I've got the files, sets is a subdirectory, set1 is a text file, and you see it's only got a couple of thousand elements in it. Some of the other sets have more. So set2 has a lot. Set3 has a lot. So these are in Nastran 10-column format, as you probably recognize. But we do also support the same things like through that Nastran supports. So you see 50990 through 52263 is a Nastran format for input sets. Okay. So those are all in the sets subdirectory. So if I just go back quickly and finish off this presentation. So then we have 4 other sets that I just showed you. Those are all included in the control file. The next entry, VFTG Palm, is defining what to do with stresses at the output stage. So here I'm using signed von Mises, SG von, and I'm going to do a mean stress correction using modified Goodman. Then the next few lines start to define loading. So VFTG sequence is the card used to specify how many events you'll have and what each event will be made up from. So in this particular case, we've got event 101 for 1 hour. That's all we have, just one event. But you can have as many events as you want, and they'll all be calculated one after the other, and the damage will be summed. In this particular case, we've just got the one event, 101. If you look at the next line, VFTG event 101, this tells us what's in that event, and it's got two contributing parts, 801 and 701. 801 is a PSD input, defined by the VFTG load 801 entry, and 701 is a static offset that's coming from a static OP2 file. So I've got 2 different inputs. One is a static input from a solution 101 Nastran run, and the second input is a random input. For that input, I need 2 things. I need the solution 111 OP2 file, which is given by exhaust weld cs01d.op2, and then I need the PSD loading, which is in a file called 201 PSD correct correlation.txt. If I go back to the analysis location, I can show you the subdirectory where the loads, the PSD files are specified. That's in a subdirectory called PSD files, and there are actually 2 matrices there, but I'm only using one. One is for correlated loads, and the other is for uncorrelated loads. That was just me messing around with the loads to see the influence of whether the loads were correlated or uncorrelated. And that might be something interesting to you, because it's possible that you've only been applying your loads in an uncorrelated way or fully correlated way before, because traditionally it's quite difficult to include the correlation properly. So that's something that can easily be investigated using these techniques. So we have the PSDs in this file. If I open one up, you'll see these are also in Nastran format, but they're double precision entries. So if you're familiar with Nastran random input, this is what's called a VRAND PS entry. And VRAND PS specifies the contributing PSD inputs to the system. This is a 3-input system, so I've got 3 direct PSDs plus 6 cross PSDs, or 3 cross PSDs, which are all complex. So altogether, I've got 9 contributing PSDs to include in this single file, and they're all written in the correct format here by, in this case, our MATLAB script, but in the future this will be done with an additional option in the CA fatigue procedure. So if you start from time histories and you want to get your PSDs created, we can do that for you very easily. Okay. I'm not going to go into any more detail on this input file, but I can do later if you want me to. Okay. So our analysis has 3 subdirectories: the sets, the PSD files, and then the third one is the Nastran input files. If I click on that subdirectory, in here I have a lot of different Nastran runs I've been working with. The one that we're going to use today, I think, is exhaust weld CS01D. I think it's D. But they're all very similar with different set requests inside. But if I open one of them up, you'll see it's a standard Nastran input file, and the frequency cards, if you want to find them, can be found in the bottom of this file. Okay. So this file has been run, and it's created the OP2 file. The OP2 file that we're going to read, CS01D, is 5.2 gigabytes. Okay. So quickly go back to the PowerPoint, just finish off the last couple of slides. So then the last part of this input control file is defining materials. So I've defined here material 1 is A6 galvanized EN, a strain life material, and it's defined by something called a VMAT FTG entry with ID 631. And if you're familiar with strain life material data, you'll see there are actually 8 data values there, 2 static properties, Young's modulus and the yield strength, and then in addition to those 2 static properties, we have 4 strain life curve parameters. Those are the first 4 entries on that EN line, and then the last 2 entries are the stress strain curve parameters. So typically 6 parameters needed for the strain life analysis. In the control file I've sent you, you'll find there are 8 other materials there, including a set of weld curves that you could use if you wanted to. I was playing around with different materials when I set the job up, and I've left them all in, so you can easily point at whichever ones you want to point at. So I'm now going to click to this live demonstration and set up and run a job. So, right, so the Nastran run is complete. The sets are created. We have our input PSD files, and so we're going to run a control file that runs the CA fatigue job, and I'm going to run something called exhaust run1.txt. So I'm opening up the same control file that I've just shown you in the PowerPoint. So this has those, for example, those 8 materials that I was talking about are all in the bottom of the file there. Okay. The sets I was talking about are all in the file there. So everything is identical to what you just saw. So to run this job, I'm going to open up a command prompt, type CAE fatigue, type the name of the control file, and press return. Now, when you run this, you'll be running it in the Altair license environment, so it'll check out Altair licenses. I'm running this in a FlexLM environment, so the first thing it did was checked out 4 FlexLM licenses. It's now picking up the frequencies from the OP2 file, and remember that's a 5 gigabyte OP2 file, and it's clicking its way through those frequencies to determine the stress intensity. It's already gone through the file once. It's now worked out the maximum stress, RMS stress in that file, and it's reprocessing based on the filtering level I set, which I set at 100, so it's repeating the whole thing to calculate the results. So there are 107 frequencies. It's now gone through once, and it's now gone through twice. It's doing damage calculations, in this case with strain life, and it's now writing the results to the CSV file and the H3D files. And in fact, that's what it'll take the longest to do. So what you've just seen in about a minute is you've seen the program read that 5 gigabyte file, process it, and write results out. Now, what I've never been able to understand is I can't physically read that file faster than that. So it kind of shows you how good the developer was that works out how to get that data out of that OP2 file, because it's incredibly fast. So we've now got, if I look on the disk, we've got a log file. We've got a CSV file. The CSV file has everything in it. It's an ASCII file with everything in. And then we've got a series of H3D files for, depending on what you want to plot, there are nodal results there, element results. If you have shells in your model, then the results will be on both the upper and lower surfaces. So what we do is we write the upper surface, we write the lower surface, and we write the worst in one file. And those also include the solids. So we're writing solids and shells in one file, and we're doing nodal and element results in one analysis. So everything's being done that you could possibly want to get hold of in that analysis. So I'm now going to go to Hyperview and pull those results in. So I'm going to read in. Where are we? Okay, so I'm reading in the exhaust.
Daniel, just to let.
Yeah.
Now I was asking if Tenneco people are having any trouble if they run the same thing that you just did.
I don't think they've had the files long enough to run this, Sridhar. So I'm anticipating that they're going to rerun this after we finish. So that's one of the reasons why I'm recording it, so that they can get hold of those files and run it locally afterwards. Because I only sent the files about an hour ago, so I don't think they'd have had time to. I don't even know if they have Nastran, and I wasn't able to send them an OptiStruct file yet.
Yeah, we do have that.
Oh, perfect. Okay, so you'll be able to run that Nastran job. You'll be able to do this really quickly. I mean, you could do it now. The Nastran job takes about probably 20 minutes, I think, on a normal machine. But then once you've got it, this job runs pretty quickly. So we're reading in the model file. We're reading in the element worst results, and in the results set, we have 20 different quantities. I'll go through and explain what each one is. So we have the various moments of response, starting off with the 0th moment, first moment, second moment, and fourth moment. Now these aren't quantities that you will probably want to use, because they're, if you like, the primary response quantities for the system. But we use those for everything we calculate. So we provide them in case there's something that you want to do special with these results. Probably the first result that's of interest to you is the RMS stress. If I click on that one, we're seeing 44 megapascals, 45 megapascals RMS stress, I think pretty well at this position here. Let's go and have a look. So it's kind of occurring on the tube. Now, I have no idea whether this model is realistic or how it's behaving, but I'm just using it as a mechanism. And the other thing that isn't done properly with this model is there's been no effort taken to model the welds as welds. So you could do that. We have weld materials, but in this particular case, we've just included them as a standard group. So that's the RMS stress. Another thing that we calculate, which is pretty unique to our approach, is we take the RMS and we ask the user, do you want to estimate a response, a peak response estimate from your random response? So if the RMS is 45 megapascals, how big roughly will the peaks be in a typical response history? So we give the user the option to output the mean value plus 5 times the RMS, or 4. He can specify the number. I put it 5, but you can make it 4. More traditionally, you'd make it 3, because 3 times the RMS corresponds with what a lot of people call Six Sigma design. Six Sigma design means plus 3 times the RMS, minus 3 times the RMS. So you can replicate that in the results sets here if you want. But just so you can see, the RMS here is 45. The mean stress that we got from our solution 101 run varies up to 43, but in the critical location you can see it's around probably 5 megapascals, so very small. So the mean plus 5 sigma stress is around 220, 230 megapascals. So it's 5 times the 45 plus a very tiny mean added on to the top. So that's quite a nice statistic that you can estimate from that. The other thing that we can do is we can take all those stresses that are linear results estimated from the linear analysis, and we can convert them into elastic plastic strains. So we can calculate the RMS strain, and I need to change the precision on the numbers now. So let me just do that. I think I have a way of doing this. Sridhar, you're judging me. Sridhar's been training me how to do all of this.
No, you're doing great now. I'm impressed already.
Okay, make current 6, and then I think I have to click on it again. Okay, I did it. Okay, so there we have the strains, the RMS strains, a maximum RMS strain of 0.000176. Now, just out of interest, the stress there was 220, so the Young's modulus is 200,000, so the linear strain estimate would have been 0.00011. So there's about 50% additional plastic response at that critical point. Now that in itself might be interesting to know how much plasticity is going on in your model at these notch positions. Other response statistics in here, we can plot the number of zero crossings. Now I need to change my make my precision back to 3. If I plot zero crossings is a number of times this thing moves backwards and forwards in 1 second. This is loaded quite a high frequency, so it's 160, roughly 160 per second. Let's see where that is. It's up here. But other parts of the model are responding less often, so their different modes are contributing to the response there. We can also plot the number of peaks per second, which is a more advanced statistic. It gives you an indication of how much dynamic behavior there is in the model, because if this number is a lot bigger than the number of zeros, then you know that you've got multimode response. And that shows up if you divide the number of peaks by the number of zeros, you get something called the irregularity factor, and that tells you the level of, or the number of resonances in various parts of your model at a particular time. So here we see the red part is pretty narrow band, which means if it's got dynamic behavior, it's single mode. And the blue part of the model, which is actually the plate of the muffler here, that's got multimode response. So there's something interesting going on there. Okay. Those are all response statistics. Then if I move on to the damage statistics, I can plot just straightforward damage. And one of the things about damage is it's a very uninteresting graphical plot, because you get a lot of damage in very local positions and nothing anywhere else. So you can see we have a lot of damage in this one place, and it doesn't give a particularly nice plot, although it's the most accurate visual plot that you can get. But if you plot log of damage, it will spread the results more, so you get a nicer plot. I'm not sure it tells you a lot more, but it's typically what people do. They will typically show the result in terms of log of damage. Okay. We also have life, so you can do log of life, for example. That'll simply be the reciprocal of damage. So log of life, we have very low life corresponding to high damage in the same location. We have another parameter here, which is margin of safety. What the margin of safety tells us is how much of the life of the structure has been used up. So if you've got 100%, it means none of the life has been used up. As that number drops, you're using up life, and when you reach 0, you've got no life left. Damage has reached 1. And as we'd expect, the very low margins of safety occur where we were seeing the high damage results earlier. So those are all fringe plots. Now I can rerun this. Now I've run this job once, and from that I'll know the critical location. I can find the element number on this fringe plot that corresponds with the highest damage. I found that out in advance, and I found that it was element 40631. So I created a second control file. This is called run1a.txt. I didn't send this one to you, but I'll send it to you later. And the only thing I've done in this control file that's different is I've added something here to reduce the output to just one element, 40631, using something called the fset3 option. And then I've changed log level to 2. Now what that's going to do, it's going to write a lot more detailed information out, but for just the one element, 40631. So if I run that job, I need to okay, I've still got the one I ran before, run18.txt. If I run that, it'll do exactly the same thing first time through, finding the maximum stress, but then it'll realize it's only doing it for one element, so it'll go slightly faster through the second process. And I've switched off, the other thing I didn't show you, I switched off the H3D output files because we don't need those. And I'm just writing a CSV plot, but it'll write some additional CSV plots that we can extract PSD information from. So it's finished, so let's have a look at the results. So it's written a couple of extra files here, one called PSD.csv and one called RCC.csv. The RCC has the rainflow count data in it. I'm not going to look at that, but I'm going to look at the PSD file. If I open that up, it gives me only for this one element, 40631, it's giving me the response PSD information at different frequencies, going from 0 up to, what's the maximum in here? 500. So from 490. So from 0 to 490, I've generated a PSD result shown in column H. Now, all I need to do is, this is a CSV file. To do this properly, I need to save this as an Excel file, and then just use a insert plot to plot that column H. I've already done that, just to save me fumbling around during this session. And the PSD plot that I get for that element is shown there. So you can request this PSD information for any output point, or all of them if you want, on that response. What we're seeing here is a very strong response for that one point at just above 40 Hertz. A little bit of response below that, and then it tails off pretty quickly by about 80 Hertz. There's not much left. There's a tiny bit at 120 Hertz, but not very much. So that's this sort of more detailed information that you get by setting log level equal to 2.